It's about just definition, right? Notation, that's what I mean. Just getting used to notation. Here's sigma t. They give you the sigma t, and the path C is parameterized by the sigma t. This is not a straight line. I think it's a parabola. In the plane z equals 1. So if you go through this plane, the curve, parabola, like this, t and t squared 1, over that, what is this thing? This integral, let me rewrite it here, integral over the path, parameterize it. If you parameterize differently, it's the same thing, right? Remember, this line integral is parameterization independent. If you put something else that starts at 0 and 1, go through exactly the same path in different way, this value will be the same. So x squared multiplied by dx. Now this one has a name. What is the name of this dx? Fancy name for that. Differential form, right? Differential form. Multiplied by dy and 1 times dz. What is this one? There's no parameterization here. They gave you the parameterization. You have to put the parameterization in there by just putting dt in there. Right? That's our exercise number 1 today. Oh, the 5th, right? 5th. Thank you. Six, 11, 15. 5 plus 6, 11, 15. Okay? Make sense? This notation is a lot easier to calculate, right? I think that's one motivation of breaking down into that form. But it really came from, what is the meaning of this one? Is again, is the line integral of a vector field, right? Where, what is the vector field here, you think? If you reinterpret it, x squared and comma xy 1. If you have that vector field, and if you dot it with sigma prime, which is dx dt and dy dt and dz dt, if you dot this one with that one, you get exactly this one, right? So they expanded us for us, and then parameterization free notation. Any question? Make sense? They often write a line integral in this way, but that's the physical meaning of it. Here's number 5. It was my mistake that I haven't introduced the kinetic energy stuff, but it does use the kinetic energy stuff in it, and that was my mistake. But also, I think the problem made a little mistake, so I'm going to give you the right interpretation and change that a little bit. So in general, this is how things work. You start from here and arrive at here. This is the path C, and particle whatever moved along that path. And there's this notion of total force, F. Maybe there's several different sources of force. F1 is acting on it, for example, this vector field in there. F2 is maybe it's my hand, wind blowing or something. Even if this is a wire to something, so the bit is moving along this wire, that wire also creates a force. For example, if the total force happened to be the 0, and if I'm claiming it moved along like this, that's a total lie. If the total force is 0, you cannot move around things like this in a curve, right? If the total force is 0, what should be the move? It's a constant speed with no change of direction, right? That must be the case. So if it is moved around like this, there's no way the total force acting on that is going to be 0. So total force, it is the sole responsibility of this curvature and moving faster and slower and all that. Okay? So the interpretation, which I did not introduce but is in the content of the section 18.1, is that if this is the total force, then the work done by this total force along that path C in that direction has reinterpretation. They can calculate this integral abstractly and come up with the following interpretation. Suppose at the beginning, and this is the velocity vector v1. Right? Velocity vector. At the end, you can't all of a sudden change the direction because you're moving along this way, right? And at the end, your terminal velocity must be pretty much in this direction, v2 vector, right? And the interpretation calculation is that these velocities are coming from this position vector at the beginning and position vector at the end, derivative. So it must be the tangential vector field, and they calculated in that book into the following using Newton's law of motion. Newton's law of motion applied only to the total force, not to the individual sources of the force. It has to be about the total force. It's half times the mass of the terminal velocity but speed squared minus the initial velocity the squared. And they calculate like this. If it's a total force, if you compute total force, work done by the total force is equal to 1/2 minus the square of the terminal speed minus 1/2 time the mass times the square of the initial speed. So we might remember 1/2 times m times the speed squared is called the kinetic energy. So this is a difference of a kinetic energy. All right. So they were saying this thing, and at the end they just put arbitrary vector in there. That is wrong. You can put arbitrary speed, but the direction must be along with the path. So I'm going to interpret this one into this problem in there. This is initial location 1, 0, 0, correct? What is the terminal location? 1, 0, 1. It is indeed directly above along the perfect, the 1, 0 never changes. Even the path is not wobbly path. This is actual straight path here. 1, 0 never changed. The only t is, so it's rising vertically. That's the path, right? And initial velocity is what? 0 at rest, right? And the terminal velocity is all of a sudden they put 1 plus 2j. At that position, what is 1 plus 2j? It's perpendicular to the vertical one, right? So I think they were trying to put some arbitrary speed in there, but they cannot put arbitrary direction in there. It just makes no sense. You can't turn the momentum around that quickly. It requires enormous amount of force to quickly turn around the momentum. So that would be the really hard force at the knocking this one at the end. So I think it's more natural to put that the terminal velocity v2 there to be still line up with the direction k vector. You can put arbitrary magnitude, right? Then it's going to make perfect sense. So what's the magnitude of that one? Root 5, right? And the magnitude of that one is a root plus a 1 squared plus 2 squared. So root 5, right? So if I match that, if I put the root 5 there, then this problem makes more sense in the physical way. You move it along like this with the initial speed 0, and then you're putting excessive force to it, and at the end you escape that path, of course, with that path along the way. Then you put that then this makes sense, and this will justify this calculation, because this calculation requires v2, v1 along the path in there. But speed can be anything. Here you can put anything, then it'll make sense. So total work done by this total force applied in there, the force field here, if I push that upward my hand, so that will be F1 plus F2, two different forces, that this dr along this vertical path upward is 1/2 times the unit mass. I think they said unit mass 1 was the terminal velocity, is a root 5, right? But the speed squared would be just 5, is that right? At the beginning is a 0. So they're claiming that the speed exiting their interpretation of this kinetic energy is 5/2. That's the total work done by the force, the total force. But there are two sources of the force. One is coming from this guy here, right? Okay? So I'm going to interpret that as a W1, the work done by that force up there, dr along that path. And if you just plug in there, that's xy comma x plus y comma 0, right? There's no, I was wrong, is a 0 in there. X plus y, right? Because j component is missing. If you calculated that, anybody remember what that was? I think that was 1. It's very simple calculation. You plug in the path in there and derivative, it turns out it's just 1. All right? And then there is additional work done by whoever is lifting that. That would be second force. I'm going to call this F2 dr. That's unknown, right? But the work is linear. If together, this will be the total work. So total work W, which is this one, is the work done by this force field out there, and the work done by my hand, for example. And that was 1. So total work done by my hand is this one minus 1, so this is 3/2. So I claim that this is awkward and weird. I think their intention was putting some arbitrary speed in there. That's okay. You can, as long as it's k, you can just put any number. This problem will make sense. All right. So also, if you look at this 1, 0 arbitrary position, 1, 0 here, 1, 0, z, right? If it is on that, if you plug it in there, is 1, 0. That's a 0 force there, right? And 1, 0, z, and there's 1, 0. That's some positive number. So this force field is actually pushing this one up there. Everywhere, this force field is actually helping to lift this one to above there. If I don't do anything at the beginning, and the rest, my hand doesn't do anything, just leave it there and rest, this force field will rise this one and arrive it here, right? So minimum work required by my hand to lift this one to that is what? 0. You don't have to do anything. This force field will do it for you. But we're actually excessively pushing this one and escaping that with the excessive amount of speed. Then this one, the difference of kinetic energy, is not the same. W is not the same as W1, which is 1 here. That means I did a lot of excessive work, so escaping with excessive speed. And then it is saying that the kinetic energy thing is picking up. Yes. All right. So this is a total force. There are two things acting on that. And if you're escaping, we don't know what happened in between. They're claiming that all that matters is the initial speed and terminal speed is going to determine the work done by this total force along that path, right? So that's pretty interesting statement, right? Doesn't matter what happened in between. It's just the initial and the terminal speed. Make sense? This doesn't make sense. But assume that rest of the part makes sense. That's what I mean. Is that okay? Yeah. And I think it should be fixed. It makes no sense physically. All right. I'm going to show you quickly why this one's true. Okay? And if you go from here to there, you will probably have a hard time to understand the argument. But if you go from here to here, this is pretty easy. It's quite strange, right? So I'm going to state that one in there like this, left-hand side, 1/2 m times, how about the v is indicating sigma prime, that's the path, so that's the terminal velocity squared, is a terminal velocity squared. Is that okay? At the beginning, times t equals a and t equals b, that's a terminal velocity vectors, right? Squared. Fair enough? Yeah. And also, we're turning this one into dot product, right? Is that okay? Because if you think about vector component x, y, z, if you dot it to itself, what do you get? X squared plus y squared z squared, right? Isn't that the square of the speed? So that's exactly how it's interpreted. Now here's the interesting part. 1/2 times the mass, and you can write this one like this: vt dot vt, right? And evaluate it at a and b. How about that? Nice trick. Everything makes sense? Yeah. Now you can put this one back into the integral. This is really unusual. We solve the integral. Why would you put that back into the integral? But this is an easier way to understand that statement. All right, doesn't it look like fundamental theorem of calculus, right? So how do you put that back into integral? You put a and b in there, right? What do you do to that inside to put it in there? You do the opposite thing. You integrate it, right? Put it back in there. What do? You differentiate, right? You differentiate and put it back in there. You know what we do? So let's differentiate this guy. Dot product differentiated. What derivative do we use? Product rule? Yeah, product rule makes sense. So let's use a product rule. It's a dot product, right? It's a dot product rule. So what do? You differentiate the first one and differentiate the second one, right? Is that right? Yeah. Now, isn't that the same thing? Yes. So I'm going to put 1/2 times m, which is constant. It doesn't change. Low speed. So if you put it in there, isn't that 2 times the, v prime dot v and dt in there, right? And these two cancel. M is a scalar, and we're going to put it on v prime. Does anybody understand why I put that on v prime? Because v prime is rate of change of a velocity, which is acceleration, right? What is m times acceleration? That's the force. Yeah, that's the Newton's law of motion. Newton's law of motion only applied to the total force, not this source of the force, not this source of force. That the final path of a movement is the only thing responsible is a total force. So it has to be the total force, and this v prime and b must be aligned with that path in there. So Newton's claiming, and I also claim that this is actually very difficult to understand if it isn't three-dimensional. It's one-dimensional easier. So that's a total force. How about v prime? That's the sigma prime there, right? Yeah, that's our thing. This is our thing, right? Backward is a lot easier. The book explains from here to there. From my experience, it's a very hard time to going from here to there. Going here to there is a lot easier, more natural. So, as far as I know, it is the motivation of them defining this kinetic energy, because it rises like this. And then second interpretation of this one is that it is linked to very close to something called potential energy. And this kinetic energy and potential energy mixed up like this, and then gives you some sort of conservation of energy. And that's the whole motivation of this whole idea of integration. It's very interesting. So right now it's linked to the kinetic energy, and it's what is surprising is that it doesn't matter how crazy your force were. All that matters in work calculation is the initial velocity and terminal velocity as you enter that path and as you exit that path, along with that path. That makes more sense, so that I alter the problem a little bit. Final remark. my deepest apology on assigning this problem, and some of you chose to do that, and probably struggle a lot because you don't have enough tools to attack those problems. All right. So what's the kinetic energy? 1/2 times mass times the square of the speed, or you can write as a v dot v. All right, and this is a difference of kinetic energy, right? Yeah. Whenever you see some difference, you can put that back into the integral, give you some crazy interpretation. This is really a non-trivial application of a fundamental theorem of calculus. You've been using it all the time. This just signifies or magnifies this. Its fundamental theorem is calculus is really strange in three-dimensional way. Straightforward calculation, but physical interpretation, it's puzzling. Makes more sense? All right. This is a summary of what we have to do. I think we started like this. Vector field there. And you're going through this path because of, this is not usually the free fall. If this is the only thing that is acting on that, and you release it with the initial speed, if that's the only thing, then this thing is totally governed by this force. This is called free fall. But maybe there's other forces acting on it. So this path is really awkward from free fall of this one. But if you calculate that, the meaning of this one is the work, the contribution of the work coming from that force field, and possibly there's other field acting on that, so creating this very different path, sigma t. And also realize that it doesn't matter how fast you're moving because of the other sources of force. The work contributing from the one source of the vector field is always the same, right? So if I change the sigma to something else, this remains the same, parameterization independence. So because of that, we expand it out like this. This is x component of the force field multiplied by the x parameterization, the derivative of x part of the parameterization, and so on in here. And this is independent of a parameterization. And then we eliminate that parameterization information. We just wrote it like this and name this one differential form, and even introduce more compact notation like this. So there's no parameterization here because it doesn't matter. That's a summary, they put it in there. And they even use this notation, but I don't use that one, so I eliminate that. All right. This is the exercise is definitely worth doing here. And we're not going to do all of them. I think what matters is you parameterize this path, right? So let's begin together. This is exercise number 2. Let's write this one down first. Integral over the path C. Let me also write down the bigger because their notation is all squeezed up like that. Sine pi x times differential dy minus, well, I should interpret it as a 0 times dx to help you the full structure. 0 times dx, is that right? Because dx is missing. And then here's a cosine of pi times y dz. That's integral. And C, they didn't give you the parameterization. They just describe it. And here's some random picture. Here's a 1, 0, 0. That's on the x-axis. And here is 0, 1, 0. That's on the y-axis. And over there, there's a 0, 0, 1. And that's the path. You start from here, going to that direction first. And at that location, you're going to change the direction, going like this. And at that point, going like that. This entire loop is called C. Alright? And they didn't give you the parameterization. Then you're going to parameterize this one, right? And put it in there. you can see probably the parameterization of this part is different from parameterization of that part. It's not like one formula, right? So I'd like to call that one C1 in there. Is that okay? I'm going to call that one. If you integrate over C1 independently, and then you parameterize this line segment, and integrate over that path independently, and the C3 over that one independently, and you calculate the work and then add them all up, that would be the same thing as doing the whole, that's explained last time. Does that make sense? So you don't have to make a connection. You can use t equals 0 and t equals 1 and calculate the work. And here t equals 0 and t equals 1 separately and calculate the work and add them all up. All right? So this is quite standard notation because what we're integrating is always the same, right? This is e. We're only changing the path. So they often write it like this. This is quite standard notation. C is equal to, there is no differential from just integral, C1 plus C2 plus C3. Okay? So that this is in question. Then you're going to calculate this one in this orientation, C2 in that orientation, C3 in that orientation. All right? So the main part of this problem is about parameterizing. Once you have a parameterization, is just plugging in an integral. That's quite simple integral. So I'd like to make this exercise number 2 just to parameterization. And the rest of the part you'll do that at home. Right? So find parameterizations of C1, C2, and C3. And let's compare answers. This is a line, right? Remember there was a method that I introduced on how to parameterize a line, beginning vector and end vector using the displacement vector, those things, V and W. Yes. All right, thank you. There it is. All right, how was it? Okay. Yeah. That's the full answer for the exercise, but let's just think about what the C1 of that thing is. So here is sine pi x dy minus cosine pi y dz, right? We calculate that, and C2 and C3 and add them all up, and that's the answer. But for this one will be t going from where to where. I forgot to put that t range. For that one, t range is from 0 to 1 always, right? When it's a 0 here, when it's 1, you go all the way to that one, going around like that. All right, so for all of them, t is 0 to 1. Not like, 0 to 1, 1 to 2, not like that. It's all separate calculation. All right. Then this one changes to 0 to 1. And sine pi times, what's x here? X is 1 minus t, right? It's 1 minus t there. Times what is dy? dy is 1, right? dy dt, that's 1. Minus cosine pi times y, that's t here. And what is dz dt? 0, so it's 0 is multiplied, dt. So it is just this integral, and you compute the integral using u substitution, because that's, better make the entire thing u substitution, and then it's going to be easier calculation. Any question?